Hello and welcome to my video on universal gravitation. So the force of gravity, force of gravitation, there you go, is a force that exists between all matter. So anything that has mass will also have its own gravitational field and therefore its own gravitational forces that it produces. So we'll talk more about gravitational fields in the next video, but for now we're talking about the force of gravity. So we're going to look at a few different examples of this. The formula above describes this force in detail. The bigger the masses, the greater the force. The smaller the masses are, the greater the force. The smaller the distance that the masses are apart, the greater the force. So basically, if you look at this formula here, as R increases, F decreases, or as M increases, either M, okay, F increases. Okay, what's crazy is that the force that the Earth exerts on you is actually the same as the force exerted by you on the Earth. So if I am being pulled down by the Earth by, not 500 newtons, whatever that is, then the Earth is actually pulling up against me by 500 newtons. Okay, this is an important fact as we look to discover new planets, because the Earth is being pulled by the sun. We are not surprised by that, hopefully. But did you know that the Earth actually pulls on the sun the same amount? So it's actually a fairly large force, but because the sun is so massive, it doesn't experience as much of an acceleration due to that. And because it doesn't experience much of an acceleration, it doesn't experience much of a radius of an orbit. The radius of the orbit is a couple hundred, somewhere around 500 kilometers over the course of a year, which is pretty darn slow. This is about 0.36 kilometers per hour, which is about 10 centimeters per second, I believe. Yeah, 10 centimeters a second. I believe that's about right. So it's not moving very quickly. It is moving. The sun is moving because of the Earth, but not very quickly. And with the Earth, it's pretty hard to detect because the Earth is fairly small. However, with any bigger planet like Jupiter, it becomes very easy to tell. So we can measure this speed using the Doppler shift of light, and that's going to be in our next unit, Doppler shift. So we're not going to worry about that right now. But the big idea here is forces are always equal and opposite. So gravity, if it's affecting one force, then it's also going to affect the other force, one mass, it's also going to affect the other mass the same way. So just like the Earth pulls on the moon actually pulls on the Earth. And it becomes a little bit more obvious with the Earth because of our tides are affected by the moon, for example. So anyways, let's continue on to the Cavendish experiment. So this image here is showing what his experiment was basically all about. Basically what they did is they started with hanging this wire. Maybe if I use red it'll be more obvious. Yes, red is clear. So he starts by hanging this wire with a known torsion force required to twist it. So as the wire twists, we know exactly how much force is required to twist it by a certain amount. So then what happens, there's a mirror here, this is a laser beam hitting the mirror. What happens is they move these big balls closer, okay, and once the big balls are close to those small balls, they're within a couple tens of centimeters, okay, then this small ball is going to move towards the big ball. And however far it moves, it's going to deflect this laser. Instead of going straight back, it's going to come out to the side somewhere, maybe like this. And by checking this deflection, that's how we know how far that the string has rotated or wire has rotated. And because we know how much force is required to rotate that wire, we're able to work backwards. And Cavendish was able to use this torsion balance to find the measurement for capital G. Capital G is the value in this formula here, this capital G here. So Cavendish had a result of approximately that, which is pretty darn good because our value nowadays is just here. And the 4 is actually as precise as we can be. After that, it's 0.0003 plus or minus 0.00015, I believe, are the numbers. So we don't even know anything beyond that value. So the 4 is the last sig dig that we actually have for capital G, for the gravitational constant is what it's called. So yeah, amazing how close this number was to our modern day result, considering the apparatus that he had. And honestly, he may have gotten a little bit lucky, but it's pretty good. It's pretty good. Okay, so there's the formula. You're going to consider it while you answer the questions below. See what you can do. See if you can answer all 4 questions. Pause the video at any time, try it out yourself, and press play when you're ready. Alright, so this first one is one of my favorite ones to start this topic off with. You find a girl at school attractive, but the only way to tell how attractive is to ask her how much she weighs. After getting slapped, you decide to simply approximate her mass to be 55 kilograms. If you weigh 68 kilograms and sit 2 meters away during physics class, how attractive is she really? So this is a very simple question, but it helps get us started. We're looking for the force of gravity between you and this girl. So basically, we're just going to put in all of the different values. So 6.67 times 10 to the negative 11. Then we're going to put in, it was 2 meters away. And we're going to put in the masses, which are 55 kilograms. Does the mass order matter? No, it doesn't matter. So just, I want you to think about it. The mass order does not make a difference if you have M1, M2, or M2 then M1. It doesn't make a difference which one's which. But anyways, this is what you should get. So now let's plug all of this stuff in. And we get an answer of 6.23645 times 10 to the 8, negative 8. So 6.2, just that, 6.2, just because of sig digs, times 10 to the negative 8 newtons. Not very attractive, hey? The girl's not as attractive as you thought, but there's another girl who sits right next to you. Oh, yes, yeah, she sits right next to you. She weighs only 50 kilograms, so she weighs less. So actually, she should be less attractive, right? But she's closer. Less attractive, more attractive. The closer they are, the more attractive they get. The more they weigh, the more attractive they get. That's how that works, right? Okay, so let's try this again. I recommend pausing the video and trying it yourself, but I'm just going to go ahead and do this now. So the other girl is 0.5, and instead of 55, she is 50. Other than that, everything else is the same. Ooh, look at that. She's more attractive. 9.1 times 10 to the negative 7 newtons. That girl is more attractive than the first girl because she's closer. That's the main thing, right? She weighs a little bit less, which actually makes her less attractive. But she's close enough that that matters more. So notice that the R is being squared, right? So a change in the R is doubly as important as a change in the mass. Okay, So, you know, maybe you're attracted to these girls, but are they attracted to you, and how much are they attracted to you? Well, actually, they're attracted to you exactly the same as you are attracted to them. Which is great. Because, you know, you always want to be attracted to the same people that are attracted to you, right? So exactly the same values, you can do the same calculation, but it doesn't matter if you switch the masses, right? That 55 could go there or here, and the 68 could go there or there. It doesn't matter as long as you have both 55 and 68. You could swap the positions of those, and you'll still get 6.2 times 10 to the negative 8. It'll be the same either way. Okay, so here you go. Here's one more question. This one's harder. You decide to repeat the Cavendish experiment with two small 2 kilogram balls suspended by a torsion balance. If the big masses are 50 kilograms and are attracted to within 5 centimeters, how precise does the torsion wire need to be in order, in other words, how much force is twisting the rope? The tricky part of this is not the initial calculation. The initial calculation is easy. Fg equals g over times m1 times m2 over r squared. This is easy. Let's try it right now, in fact. Okay, this is 0, 1 because it's, no, 5 centimeters, 0, 5. Okay, and then these ones are 2 kilograms and 50 kilograms. Okay, enter. So we get a value of 2.668. So 2.668 times 10 to the negative 6 newtons. Is that the correct amount of force twisting the rope? No. You have to be careful here because there are two small balls. So let's go up. Notice that there's a force here in green, right? And there's a force here in green. So the forces are actually being doubled. So be very careful about that. Very careful because the forces are doubled. So we're going to times by 2. So times by 2, we get 5.336. Which is actually, just in terms of sig digs, we really have 1 sig dig, so 5 times 10 to the negative 6 newtons. So if you want to be able to measure this force, you need to be able to be at least this precise. So you can imagine how Cavendish would have had to have a very, very carefully built apparatus to have that type of precision on a wire. So, and then to measure how much force is actually being used, like with that, or how far it's twisted with the laser, right? So there's multiple levels of precision here. Anyways, yeah, universal gravitation, the idea that there's a gravitational force between every single piece of matter, anything that has mass, and forces are always equal and opposite. So then you can do calculations based off of this formula here. You should know about Cavendish experiment for the test as well. Yeah, I hope this video helps you, and good luck.